So let's look at free energy diagrams. So free energy diagrams and trying to understand what they tell us. So the first kind of two terms we used, remember, were kinetics. And thermodynamics. So what does kinetics tell us? What does it have to do with? How fast products form. Which would have to do with what part of a free energy diagram? The activation energy, the transition states, right? So it has to do with the transition states. And in transition states, do we have fully formed bonds? No fully formed bonds in transition states. So kinetics asks how fast. It has to do with the hills, the transition states. What about thermodynamics? What does that ask? How much product? So what's it more concerned with? Change in delta G naught, right? So how stable the products are. All right, so let's draw a free energy diagram. So I have a free energy diagram, and I'm telling you I'm going to form a thermodynamic product is going to form. Right? That I'm going to form a lot of, according to thermodynamics, I'm going to form a lot of this product. So here's my starting material. Where should I draw the product? Should it be higher in energy or lower in energy if I'm going to get a lot of it? Lower. Good. Notice how that doesn't tell us anything about, right, how we got there. It doesn't tell us anything about how we got there. Right? Now, if we have a really high hill, right, that's a transition state, and that tells us how fast things go. Right? That'll tell us how fast the reaction will go. Right? How much energy it takes to get to this product. Just because a product's more stable than the starting material doesn't mean you're going to form a lot of it. Right? Diamonds are not the most stable form of carbon. Right? But the activation energy needed to get to that other different form of carbon is super, super high. So the rate is super, super slow. Right? So even though diamonds aren't the thermodynamic form product of carbon, they still are pretty stable. Look at it. Let's do a problem and do a free energy diagram and see how many hills and all that kind of stuff we have. So let's do so we have an alkene reacting with HCl in methanol. Right? First step, number of carbons, 1, 2, 3, 4, 5. What's my nucleophile? The pi bond, right? Specifically the pi bond. Break HCl. Break the HCl bond. Now I have a choice where to put my plus charge. I'm going to put it on carbon 2. Why? Secondary. And why is secondary more stable? Right? So if you just say secondary, that's not going to get you all the points. You need to say hyperconjugation.
Isn't there a strain though?
Yep, so let's take a step back. So once we form a carbocation, we always got to think, right? Can we rearrange it to form something more stable?
Yeah.
And if we can, we will. So we have a choice here. We could do a couple things. We could do a hydride shift the hydrogen that's on carbon 3 over, and that would give us a tertiary carbocation, but that might not be the best. Let's take a look at that possibility, that 1,2 H shift. Why is this not so great? What's the hybridization state of carbon-3? sp2. What are the bond angles for an sp2 hybridized carbon? 120. What are the bond angles for a triangle? The highest they could be is what? Right? Highest they could be is 90, but right. But even that, this is not going to be very happy, right? You gonna want to have a carbocation there? No. So this will not happen. What else could happen? If we can't do a hydride shift, what other kind of shift could we do? It's possible. A methyl or just a sigma bond shift. Right? What if we shifted bond 3 to 5?
Why can't the hydride shift work?
Hydride shift won't work because we form a really less stable carbocation than we started with. This would be a carbocation, right? This would be a triangle with 120 degree bond angle, which is impossible, right? So it would be really unstable, right? Versus just secondary. So what if we shifted 5 to 3? So what bond did we make here? What two carbons are now bonded? 5 and 2. So let's just draw it like that. 5 and 2. What else is 2 bonded to? 2 is also bonded to carbon 3. Good. What else is 2 bonded to? 1. So there's 1. What is carbon 3 bonded to? 4. And what is 4 bonded to? 5. Now, there's a plus charge up here. That means there has to be a plus charge on our products. Which carbon has the plus charge? Carbon 3 does. Good. Now, it's not like this is great either, right? To be honest, this one's better than this though, right? Because what's the bond angle in a square? 90, right? Which is closer than 60, but still not great, right? So let's just say this does this anyways though. We'll give it the benefit of the doubt. It might just stay like this, but we'll say it opens up and this is better. But actually, you know what? Actually, I take that back. No, it's not better. Why is it not better? Would this happen?
It's
Still secondary, and now the bond angle is actually worse. So would it do a rearrangement? No. So I don't think it's going to do this either. Does anybody see why it won't do that? Right? Hybridization state matters, right? Carbocation's hybridization state is sp2 hybridized. Bond angles are 120. A triangle and a square certainly don't want to have bond angles that are 120. But this carbocation will. Okay? So the next thing that's going to happen, since none of that's going to happen, what's my nucleophile most likely to attack? What's my best nucleophile? Chlorine, Cl- or methanol? Which one's a better nucleophile? Chlorine is a better nucleophile. But how much methanol do we have? Remember, if it's underneath the arrow, it's a solvent, right? So do we have a lot of it? So what's going to attack? The methanol. What specific part is the nucleophile? The lone pairs on the oxygen is specifically the nucleophile, right? Did we break any bonds when we did this step?
No.
This is the trap people get into. They really, 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 really want to they really want to break this CO bond for some reason. There's no CO bond breaking. 2, 3, 4, 5. There's O. There's an H still, right? This oxygen is still bonded to hydrogen and the carbon. So where's our plus charge be at? On the oxygen. Right, and then the last step. The last step is the electrons between the OH go to the oxygen. And we get our final product, which is an ether and H+. We number our carbons 1, 2, 3, 4, 5. So now let's look at what this looks like in a free energy diagram. So our free energy diagram, we'll say our starting materials are here, right? How high should I make the first hill?
Probably high.
Why?
Carbocations are difficult.
Why are carbocations difficult to form? Why are carbocations unstable?
There's the bond plus charge.
They have a plus charge. They have 3 bonds. What's the first rule of Lewis dot structures?
Octet.
Octet. Does the carbocation have a full octet? No. So that's why it makes it unstable. So we say this is intermediate A. This would be intermediate B, and then of course this is the product. Right? Every arrow I have is a hill. Right? Every arrow I have every reaction arrow I have is a hill. So how many hills should I have? 3. And how many intermediates do I have? 2. So I should have 2 valleys. So A is high in energy. Would B be higher or lower energy than A? Lower. Why? Why is it more stable? Why is B more stable than A? What's the first rule of those dot structures? Does everybody in B have a full octet? Does everybody in A? No. So here's A. Here's B. And go to products. We want to label our transition states. And our intermediates. So there's 3 hills, 2 intermediates. Let's work backwards for one. BH3. Then part 2 is OH minus H2O2. And the product is going to be OH. So the first thing I would do, if you see, so you know you have to go through the borohydride hydroboration and oxidation mechanism. So you're going to add BH2 at some point in a hydrogen. And you're also going to add OH. You're going to replace the BH2 with an OH minus at some point. You also know that when you have the borohydride, you put it on the less substituted carbon of an alkene, right? So if we number our carbons, 3, 4, and 5, right? All your start materials in this chapter, this unit, have all been what? For all these reactions, what is your major functional group? Alkenes, right? So again, here you know this product is going to come from a alkene, right? So you know everything has to start with an alkene. So if you're going to use BH3, where would you want to put your alkene? Between 1 and 2, I think, right? Between 1 and 2, right? Find out where the group you added is at, right? And that means that had to come from the functional group, right? In this case, the functional group would have to be the alkene. All right, so if we number it 1, 2, 3, 4, and 5, right? We know with BH3, we end up on the less substituted carbon. The boron ends up less substituted carbon because of sterics. Right? So let's draw, now we can go ahead and draw the mechanism. Right? I'll go ahead and go forward with it. So the biggest thing, the easiest thing I like to do is draw the boron, showing that it's, what hybridization state is BH3? sp2. Right? Does BH3 have a full octet? No. Does it want a full octet? Sure. Right? What's my nucleophile in this case? Pi bond. What's my electrophile? The empty p orbital. Right? So as that attacks, though, as that pi bond attacks, at the same time, right, this hydrogen attacks carbon 2. Right? At the same time. So one way, if you want to look at it, right, to draw the wedges and hatches, put the BH2 here, and put the H here. Now, what's the hybridization state of carbon 1 and carbon 2? What are those hybridization states? They're the same. Or what are they? Carbon 2 is what hybridization state?
So I'm confused as to why we have wedges and hatchets when it's not a stereo center.
I'm just showing it for point of clarification, to show that, to make sure you understand how it's coming in, right? Because it's BH3 is this is a cis addition, both the H and the BH2 end up on the same side, right?
No,
So what's the question is, what's the hybridization state of carbon 2?
SP2,
sp2, so what's its geometry?
120, or trigonometric.
Trigonoplanar, so it's flat. So, right, so the boron, I have it shown here as the boron, the BH3 coming on the bottom of that, but could have also came from the top? Yeah, so that other, right, if it's pertinent, the other enantiomer will be formed. In this case, right, we're not forming an enantiomer, right, but I'm just drawing these I'm drawing it out like this, just to show that it still has a cis addition, even though we don't get, right, an asymmetric center.
So on a test, would you want both those answers?
If I specifically asked for all the intermediates, technically they're no different. So if you did it from the top, it's the same as this actually. So unless they have asymmetric centers, the intermediates aren't different, just like the products aren't different. Right. So the final step here, right? So that's all step 1. Step 2 then is just the OH minus in the hydrogen peroxide. We didn't ask you guys to know this, remember? And that gets us to the product. And the OH replaces the BH2 on the same side, right? So they end up being the same side. Good point. 1, 2, 3, 4, 5. So carbon 2 gets a new hydrogen. This hydrogen right here is this hydrogen, right? There were 2 hydrogens here to start off with. Those are those 2. There was 1 here, and that's this. Let's try another working backwards problem. Use black. So let's say this is your product. They're saying what reagents are you using and what starting material. Right? Okay. First thing we do is number our carbons. 1, 2, 3, 4, and 5. So what's one way you guys, what's the only way you guys know how to add 1 chlorine? What reagents do you have to use? All right, so this is going to have to be HCl. And where is this, that, right, what's our starting material going to probably be? Not probably, it has to be, right? We've only done alkenes. So where should we put the double bond?
Between 3 and 2.
We could put it between 3 and 2. Yep. So we could have this be our starting material. What other starting material could we have? We could put the double bond between 3 and 4. What other starting material could we have? 3 and 5 would work.
So can we just pick one of these and say what's the starting material?
That's one, but there's another one we could have too. We also could have the double bond between 1 and 2. Right? This one has to, the one between here.
CHM tells us there's no way we should miss this question.
Well, so this one, remember, is going to come. This one's going to have to be a rearrangement. Now, where this gets hard is what if I had an ethyl group here and we formed an asymmetric center? Then all these products won't necessarily work. Because then I need to know, right, is a double bond cis or trans? That's going to make a difference of what stereocenter I form here. So as I have it right now, it's very simple. Right? But the next unit we work on is we're going to start thinking about, right, how cis and trans, really thinking about how cis and trans would affect the stereocenter. So all these would work for this unit. Unit 4 is not going to be so easy. Make sense? Let's do an O's analysis problem. So we have O3. All right, let's do, right? So what are the products here? The first thing we're going to need to do, number your carbons. 1, 2, 3, 4, 5, 6, and 7, right? And so what happens with the O3? It takes an alkene, a double bond, and does what to it? splits it. It's like scissors, right? Scissors cutting it. And I think there's a picture in your book still of scissors. Right? It cuts it. Right? So we don't need a mechanism for this. All it's going to do is take an alkene and stick an oxygen and make acetyl bond O on whatever was an alkene. It's not going to be a carbonyl group. Acetyl bond O.
Does that to all the alkenes?
It does that to all the alkenes, every last one of them.
When they make a ring, but it didn't ring that.
So an aromatic ring, it won't do that too, because an aromatic ring is really stable, right? A benzene ring is really stable. So the easiest way to do this is literally just draw it like this. Or if I numbered my carbons, this was carbon 2 and 3, right? 2 and 3 right here had the pi bond between them. Now they have 2 oxygens, they have carbonyl groups. 2 was bonded to carbon 1, and it was also bonded to 7. What kind of functional group is 7? What kind of functional group is this? What kind of functional group is this? It's a carbonyl. That's the big umbrella. It's a what? Aldehyde. Right, it's an aldehyde. Is there a hydrogen right here?
Yes.
Is there a hydrogen on carbon 7? There we go. 4, 5, and 6. What kind of functional group is this one? What kind of functional group is this one? Ketone. This one? Well, this whole thing. What is this? A ring. Okay. How many carbons in the ring? Cyclopentadiene. Thank you. Diene. All right. Everybody make sense how we get to this point where we have these carbonyl groups, how they break up? Good. Let's do a Fischer projection. So if something looks like this, where it has, oh gosh, I, OH, H, and methyl, right? So you'll see something flat like this, but what it really looks like, remember, is the things on the horizontal are coming out at you. The things on the vertical line are going away. Coming out, going away. So first thing you need to do is draw it like this, right? Draw in your wedges and hatches. And then at this point you just need to rank things, right? So first you got to decide, are both of these carbons, if you call this carbon here and this carbon here, they both have 4 different things bonded to them? Are they both sp3 hybridized and have 4 different things bonded to them? Good. So let's rank. Let's do the top one first. What's the lowest priority? H, so we'll call that one 4. What's the highest? Good. What's number 2? Carbon at the bottom. Good. And 3 would have to be this one. So now you take out your handy dandy red, white, and blue. Let's take a second and do that. All right, so after much deliberation, we've decided that this one is S. Right? Red, white, and blue. Let's do the next one. So we'll do this in blue. What's our lowest priority on this carbon here now? Hydrogen's 4. What's our highest? Iodine's 1. Right? Greater atomic number, higher ranking. What's Br? 2. And the other one's 3. So let's go take our models out and see if we can get this one. So after less deliberation, we decide this one was S as well. All right, so that's how we draw Fischer projections and then do an R and S.